Welcome back to the Public Exam Review on Unit 8, Chapter 8, dealing with logarithmic functions. In this review session, we will look at the inverses of exponential and logarithmic functions. Here we will focus on demonstrating that a logarithmic function is the inverse of an exponential function. In this example, we will graph an exponential function and its inverse. So we are asked, what is the equation of f inverse of x if f of x is equal to 1/2 raised to the power of x? This is the original function, where f of x is equal to 1/2 to the power of x. In your study of Chapter 7 in this course, you learned that this function is an exponential function, and because the value of c is between 0 and 1, the graph should represent that of exponential decay. In order to find the equation of the inverse function, there are two steps involved. The first step, we need to switch x and y. Therefore, f of x is really a fancy way for writing y, so we have y equals 1/2 to the power of x. When you switch x and y, you end up with x equals 1/2 raised to the power of y. The second step in determining the inverse function is to solve for y. In order to solve that equation for y, you need to change it to logarithmic form. So we have y is equal to the log of x to the base of 1/2. That gives us the equation of your inverse function. So f inverse of x is equal to the log of x to base 1/2. Next, we are asked to sketch the graphs of the original function and f inverse of x on the same coordinate plane. So we are looking at the graph of f of x, which is equal to 1/2 raised to the power of x. If we assign values to x, then we can solve for f of x, which is equal to y. So when x is equal to a -2, 1/2 raised to the power of -2 is equal to 2 squared, which is equal to 4. So you have the point -2 and 4 on your graph. When x is a -1, the value of y would equal a +2. So you have the point -1 and 2. When x is 0, anything raised to the power of 0 will equal 1. So you have the point 0, 1. When x is 1, y will equal 1/2. And when x is 2, y will equal 1/4. Notice that these values of y are approaching the x-axis, but they will not touch it. So the x-axis here represents a horizontal asymptote. So let's connect these points, thereby forming an exponential decay type of curve. So the graph of that function is y equals 1/2 raised to the power of x. In order to graph the inverse function, let's just change the colors there for that. In order to graph the inverse function, all we need to do is switch the values of x and y in the original table of values. So to graph f inverse of x equals the log of x to the base of 1/2. A -2 and 4 will now become 4 and -2. The point -1 and 2 becomes 2 and -1. Then you have the point 1 and 0, the point 1/2 and 1, and the point 1/4 and 2. Connecting these points, you get the graph of the inverse function. So this is the graph of y equals the log of x to a base of 1/2. It is important to note that when you are graphing functions and their inverses, that both of these graphs will be reflections of each other in the line y equals x. and that is true in this example. We are also asked here for the domain and the range of the original function, as well as the domain and the range of the inverse function. When you look at the original function, you can see there that the domain will be all values of x, such that x belongs to the set of real numbers. The range, however, will be all values of y that are greater than 0. And again, y belongs to the set of real numbers. When you're working with functions and their inverses, note that the domain of the original function will be the same as the range of the inverse function. So the range of the inverse function are all values of y belonging to the set of real numbers. And the range of the original function becomes the domain of the inverse function. So here, for the domain of the inverse function will be all values of x that are greater than 0, and x belongs to the set of real numbers. That's why we make the switch with x and y. So the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. Let's look at another example where we will graph a logarithmic function and its inverse. So first we are asked, what is the equation of the inverse function if the original function f of x is equal to the log of x to base 3? Again, we follow the same procedure. In order to find the equation of the inverse function, the first thing we do is we switch x and y. So when you switch x and y, remembering that f of x is just another way of writing y, we have x is equal to the log of y to base 3. The second step is we are asked to solve for y. So in solving for y, we need to convert this logarithmic equation into an exponential form. So we have y equals 3 raised to the power of x. This value for y gives us the equation of our inverse function. So note that the inverse of a logarithmic function is an exponential function and vice versa. In the previous example, the inverse of an exponential function is a logarithmic function. So now we are asked to sketch the graphs of the original function f of x and f inverse of x on the same coordinate plane. In order to do the first graph, we have y is equal to the log of x to base 3. In order to graph that function, we need to convert it to exponential form. So we would have 3 raised to the power of y is equal to x. In this case, y is the independent variable. So we will assign values to y and solve for x in order to sketch its graph. So assigning values to y, or f of x, we will use a -2, -1, 0, 1, and 2. And then we will solve for x for each of those y values. So when y is a -2, 3 raised to the power of a -2 is 1/9. So you have the point 1/9 and -2. When y is a -1, x will equal 1/3. So we have 1/3 and a -1. You just estimate where those points are as close to the y-axis as you possibly can get. When y is 0, x will equal 1. So we have the point 1 and 0. When y is 1, x is equal to 3. And when y is equal to 2, 3 squared is 9. So you have the point 9 and 2 on the graph of the original function. Connecting these points, you get the graph of your logarithmic function. So that is the graph of f of x, which is equal to the log of x to base 3. Next, we will graph the inverse function. The inverse function in this case, f inverse of x, is equal to 3 raised to the power of x. So we can switch the values in the previous table. So when x is a -2, y will be 1/9. So you got the point -2 and 1 over 9. When x is a -1, f inverse of x will be 1/3. Then you have the point 0 and 1, the point 1 and 3, and the point 2 and 9. Connecting these points, notice that the graph represents that of an exponential growth curve. So that is the graph of f inverse of x, which is an exponential growth, y equals 3 to the power of x. And similarly, as with all functions and their inverses, the two graphs will be reflections of each other in the line y equals x. Once again, we are asked for the domain and the range of the original function. The domain of the original function, you can literally put your finger on the x-axis and note that this graph will have all values of x greater than 0. That also confirms the fact, by the way, that when you are taking the log of x, that argument x has to be positive, because we cannot take the log of 0 or the log of a negative number. The range of this function are all values of y belonging to the set of real numbers. The domain of the inverse function are all values of x belonging to the set of real numbers. Notice that that's the same as the range of the original function. And the range of the inverse are all values of y greater than 0, where y belongs to the set of reals. So that corresponds with the domain of the original function. Let's look at some multiple choice items that could potentially be asked on your public exam. Here we are asked, what is the inverse of the function y equals 3 to the x? The key word there is inverse of the function. The minute you see the word inverse, there are 2 steps involved. Number 1, we have to switch x and y. In doing so, we end up with x equals 3 raised to the power of y. The second step involves solving that equation for y. And in order to do so, you have to convert it to logarithmic form. So we have y equals the log of x to base 3. Keep in mind that when you're switching from exponential form to logarithmic form, that the base to the power is the same as the base to your logarithm. So that's another way of helping to remember how to switch from one form to another. So this answer then corresponds with D as your multiple choice answer. In example 2, we are asked what is the inverse of y equals a raised to the power of x. Similarly, note the key word here is still inverse. So in order to do that, the first step involves switching x and y. So we have x is equal to a raised to the power of y. The second step, we are asked to solve for y. And in order to do so, we again convert it to logarithmic form. So it will be y equals the log of x to base a. And that answer corresponds with B as our multiple choice answer. That is the inverse of y equals a raised to the power of x. In the next example, it says, which of the following graphs best represents the inverse of the function y equals 1/3 raised to the power of x? So in this case, again, we are looking at the inverse of this function. The inverse of the function y equals 1/3 raised to the power of x. So we can again look at switching. If we switch the x and the y values, then we should get some coordinates of some points on the new graph. So if we look at y equals 1/3 raised to the power of x, and if we pick some values in the table on that graph, we can just pick a couple of values to help us. So if you take negative 2, 1/3 raised to the power of negative 2 is the same as 3 squared, which is 9. So that means on the inverse graph, when we switch x and y, you have x equals 1/3 raised to the power of y. So that point will correspond with 9 and a negative 2. The point 9 and negative 2 will only be found on this first graph there in part A. Let's just verify that using a couple of other points. When x is a negative 1 on the original graph, 1/3 raised to the power of a negative 1 is the same as 3 raised to the power of 1, or just 3. So then when you switch the x and the y values, 3 and negative 1 has to occur on the new graph. And that is true for part A. Similarly, 0 and 1 will get mapped onto 1 and 0. The point 1 and 1/3 will get mapped onto 1/3 and 1. So that confirms that part A is the solution for this example. In example 4, which is the inverse of this graph? Again, we're dealing with inverse functions, and what I think we should use here in this example is consideration of a reflection in the line y equals x. If you look at the line y equals x, and you're looking for a reflection of the original graph, the reflection will be as follows. The reflection in the graph, it will go very, very close to the y-axis, but it will not touch it. So the graph of your inverse function should look something like that if the original function f of x is given. So the only graph that corresponds with that one is D as a multiple choice answer. So D is the multiple choice answer for that example. And again, you could verify that using some points as well. Like if you look at some points on the original graph, and just let's say that the point -1 and 4 is on the original graph. So if -1 and 4 is on the original graph of f of x, then that should correspond with 4 and -1 on the graph of the inverse function. And in the case there, you have 4 and -1 is approximately this point right here. All right, so that again confirms that D is the multiple choice answer. And finally, we are asked, we are told that the range of the inverse function, f inverse of x, of f of x is equal to the log of x to base 4. So the question here is asking for the range of the inverse function. That's what the question is asking. And we have to remember that the range of the inverse is the same as the domain of the original function. So all we are given here is that the original function, f of x, is equal to the log of x to base 4. At this point, it is important to remember that you cannot take the log of 0 or the log of a negative number. Therefore, we know that x has to be greater than 0, and x belongs to the set of real numbers. So that is the domain of f of x. Therefore, the range of your inverse function will be all values of y such that y is greater than 0 and y belongs to the set of real numbers. So that answer corresponds with A as your multiple choice answer. Y is greater than 0. Just remember that the domain of the original function becomes the range of the inverse, and that will enable you to determine the range of the inverse function. As a summary then of what we've covered in this presentation, the inverse of the exponential function y equals c raised to the power of x. C has to be greater than 0 and c cannot equal 1. So the inverse of that is when we switch x and y. X is equal to c raised to the power of y. Or in logarithmic form, y is equal to the log of x to base c. Conversely, the inverse of the logarithmic function, y equals the log of x to base c. C has to be greater than 0, and c cannot equal 1. So when we switch the x and y values, we get x is equal to the log of y to base c. Converting that to an equivalent exponential form, we have c raised to the power of x is equal to y. The graphs of an exponential function and its inverse logarithmic function are reflections of each other in the line y equals x. So when you talk about the graph of an original function and its inverse, they are reflections of each other in the line y equals x as shown in this diagram. So here we have y equals 2 raised to the power of x. The inverse of that function is y equals the log of x to base 2. And there's the line y equals x, and you can clearly see that the two graphs reflect each other in the line y equals x. For the logarithmic function, y equals the log of x to base c, where c is greater than 0 and c cannot equal 1, the domain will always be all values of x that are greater than 0, where x belongs to the set of real numbers. The range is all values of y such that y belongs to the set of real numbers. The x-intercept will always be at x equals 1. I prefer to give the coordinates 1 and 0 for the x-intercept. And we also have a vertical asymptote is x equals 0 or the y-axis. That's where the graph will approach, but it will never, ever, ever touch the y-axis. So that's it for exponential functions and their inverses, as well as the inverses of logarithmic functions. Thank you for your time and your attention.